This is the first course in part one of the OMNI course and MFPH as well, course on One Health related modeling. And as I'm giving the first lecture, I'll spend a few minutes first going over the course organization and then giving you a very brief introduction to mathematical epidemiology. So just as a matter of information, I'm trying out that chroma key type thing, and it might take a little while for me to find a good setting. Hopefully later lectures will be better. Okay, my name is Julien Rino. I'm from the Department of Mathematics and the Data Science Nexus at the University of Manitoba. So as this implies, I'm interested in, a prof of mathematics, but I'm also interested in data-related aspects. So very briefly, what I'm going to cover in this very brief lecture is, first of all, a brief summary of what the course will contain as overall, I mean. And then I'll talk about the lectures, the two remaining lectures I'll give for this week, make a few remarks about terminology in epidemiology, and then a very brief history of mathematical epidemiology. So part one of the course, the title is One Health Modeling for Emerging Infectious Diseases. And so this is what you will be following for a couple of months until essentially the end of January 2023. The course contains one introductory part, which is going to last 3 weeks, and then 3 themes. So the themes are coronaviruses, influenza, and environmental transmission of pathogens. Each block is 3 weeks, and I should point out, except for the introduction, the third week of the course will always consist in group work, and at the end, presentation of the result of group work. The details, and I should point that out here, the details in each section, each theme will be articulated by the people teaching that theme. So the introduction is taught by several of us, but then afterwards Marina will teach coronaviruses, Asefa will teach influenza, and I will teach the last part, the environmental transmission part. There are tutorials. Each instructor will tell you how things will work in that regard. Now, what am I going to talk about this week? I'm going to give you a very brief introduction to mathematical epidemiology, and that's the remainder of these slides, and as you'll see, that goes very quickly. And then I will have 2 separate videos for lectures. One will have an introduction to compartmental models in epidemiology, and I will only present 2 models in there. The idea being that some of you know Math Epi very well, some of you might not know it that well, and the purpose of the course is to bring you up to speed on these aspects. And so here I'm just going to brush the surface of what is available, what people do, and then I will spend some time presenting some aspects which I think are important in a course like this one, which is numerical methods. And we're not going to look at the specifics of the numerics, but more from a computational point of view, what can you use and how you will use these. And I will make the point right away that I will be using R. Other instructors might use other programs, but my personal favorite is R, and that's what you'll see in these notes. So first of all, before going into MathEpi per se, let me take a few minutes to talk about terminology, because I think it's important. We, as mathematicians, tend to use some terms in a way that is sometimes not the same as what is used by people in other domains. And so I think it's important to realize this. And so, for instance, so this one is, we use the proper term, but you will see misuses of the terms. So incidence is the number of new cases in a population generated within a certain time period. Whereas prevalence is the number of cases of a disease that are present in a population at a given moment in time. And that is an important distinction, because a lot of people make the mistake often of using, we'll have a variable very typically called I of t. And a lot of people use these variables and they call it the incidence. It is not, I of t is not the incidence, it's the prevalence. Okay, the incidence is the rate at which new cases are generated. So it's it's not a state variable, it's a combination of state variables. That's important. Another interesting quirk of MathEpi comes from the way somebody way back, I believe, defined what they called exposed. So in a mathematical epidemiology point of view, an exposed is someone who has contracted the disease but is not yet infected with the disease, or infectious with the disease. So they're not showing symptoms. And typically that's why we call an SEIR model. But in real epidemiology, someone who's been exposed to the disease is someone who has come into contact with the disease, but not in the sense of they've run into someone who's bearing the disease, or they've been contaminated, or they've come into contact with an environment that is bearing of the disease, but they are not necessarily infected with the disease. And that's an important distinction. I'll make the remark that interestingly, I some years back embarked on a sort of crusade to make modelers realize that it would be better to use latent or incubating as a name rather than exposed. But it turns out that real epidemiologists have become familiar enough with the terminology of SEIR models that they don't care usually. Epidemic curves is something you will see a lot of in this course, and I'll just point out that what they are, they're used to record occurrences of new cases as a function of time, and typically you will see two types. You will see something like this. I've disappeared behind my, let me see if I can make myself move to the top. Nope, I cannot make myself move to the top. It looks like I should be able to. Or I should be able to move this to the back. Okay, no, apparently I can disappear behind my slides. Okay, good. So these are the type of data that you will see most of the time at the beginning of an epidemic. So each little spot in that curve represents one person, whereas later on during the epidemic, the numbers may become too large for this to hold, and you'll typically see a curve being used instead of the little bars, although sometimes people will show the little bars. Okay, so that's epidemic curves, which we'll come back during the course. Some more terminology, which I think is important. An epidemic is diseases, we call epidemic diseases that are visited upon a population. And as difference, we call pandemic an epidemic that has spread across a large region. Typically, we think of pandemics as representing multiple continents or worldwide spread, and I will come back to that in a second. Now, an endemic is a disease that resides within a population. And interestingly, we don't say pandemic, okay? We just talk of endemic or epidemic or endemic, and a pandemic is an epidemic that's worldwide, but if a disease has propagated worldwide and is present worldwide, we wouldn't say endemic. And just as a remark, what I was saying before, these are, for instance, the WHO pandemic phases for influenza, but which were used essentially since, for instance, for COVID. And you can see that there are 6 levels to a pandemic declaration. Typically, phases 1 and 2 are phases. So, of course, the description that I'm giving here is in terms of influenza. So there's no influenza virus causing circulating, etc. And then when things get more critical, the text is not showing there. Okay, this is a pandemic alert. Number 5 is that the virus has been detected in 2 countries in 1 WHO region, and we finally get to the full-blown pandemic stage when we have the virus that's present in several WHO regions. And just a remark in passing, that's quite interesting. You can see that WHO regions are a little weird for some things because, for instance, if you look at the Pan American Health Organization region, which is the entirety of the American continent, so north and south. If you have a disease that's spreading both in the southern part and the northern part of the continent, you should be worried in a way, because if I have influenza spreading at the same time in the southern and northern hemisphere, it is quite critical. But nonetheless, that would only be 1 WHO region in that case. Okay, so these terms being articulated, let me move on to mathematical epidemiology. So I'll point out that this is an old domain, okay? It's been around for quite some time, but it's only become a thing, so to speak, in recent years, okay? Actually, the first, what's considered the first epi paper, math epi paper, was written by Daniel Bernoulli in 1760, so quite some time back. And by the way, I'll point out, my slides are, I will distribute them and you can click on stuff. The links are active. They're web pages, not PDFs. And you can access the files here. It's a model about smallpox, interestingly, with monkeypox having emerged globally recently. Here, this was a paper about petite vérole, which is smallpox. Another sort of well-known phase in mathematical modeling and epidemiology is Ross. So Ronald Ross is the person who observed malaria the first time. So he contaminated mosquitoes by feeding them on someone who was positive with malaria and observed malaria. And that got him the Nobel Prize for Medicine. But interestingly, Ross was very keen on mathematical modeling. So a lot of his work after 1900s involves mathematical considerations on how to control malaria and so on, using some techniques from mathematics. Probably the most well-known paper in mathematical epidemiology is the paper of Kermack and McKendrick in 1927. I'll come back to that one in the following video, so I won't spend a lot of time here. I'll just point out that this is not a single paper, and the most well-known model out of the first of a series of paper is a very tiny part of what they did. So I'll come back to that. And there was some activity, and I mean, there was a decent amount of activity on MathEpi for many years, but not that much, essentially, until the 1990s. Roughly, when you look at publications, you can see that in the 1990s, things really started to pick up on the mathematical modeling side. And as you are probably well aware, since the beginning of COVID, things have been absolutely insane in terms of the number of publications. Let me give you what I think are a few landmarks in MathEpi, and I will point out that these are landmarks in my biased opinion. So besides the papers I've already talked about, you have a paper of, well, a book actually by MacDonald in 1957 about the epidemiology and control of malaria, which was extremely influential. As a transport epidemiologist, I am mostly interested in how diseases move about in space and time. For me, there's a paper that's sort of started an entire domain. It's a paper of Barorian, Ratchev, and several others who were in the USSR, and they looked at a deterministic epidemic model for spread within of influenza for the USSR. It's a very interesting model. There's a book. LNBM is Lecture Notes in Biomathematics. These are the green books. It's a series, but unfortunately is not published anymore. So there's a book by Heathcote and York about gonorrhea transmission dynamics, which is from 1984, which I think is a very important book in a sense, because they really laid out the principles of how one would analyze a mathematical model of epidemics. There's a lot that's been done since, and they were summarizing what was happening at the time, but it's still important. There's a book of Anderson and May that I personally don't like so much, but that is really important. That came out in 91, I believe, and that sort of really popularized the topic in less mathematical circles. So the advantage, the sort of the benefit of the book of Anderson and May is that it really made the topic more available to people that were not hardcore analysis people. There's a book of Capasso, it's also a lecture notes in biomathematics, that I think is really nice because it articulates some very systemic approaches to MathEpi, in the sense that he really considers them from the angle of systems, as people in control theory, for instance, tend to think of problems, and this brings a lot of power in terms of mathematical tools that can be used. There's a very well-known article in Science Review by Herb Heathcote from 2000, which was extremely influential in getting MathEpi where it is now. And I'll, some sort of a bias because these are two very good friends of mine, but I'll point out that there's a paper of Van den Driesch and Watmore, we're both Canadians, which is extremely influential in the sense that it provides a mechanism for computing the basic reproduction number that we'll see later in the other lectures. It's an algorithm for computing this important quantity, and that paper was extremely influential in the sense that it provided a lot of people with a sort of guide as to how to compute this number. Now, more recently than Bernoulli and others, there's some models in computational epidemiology, and I would say that's a more recent trend. There's that paper of Baroyan and Ratchev that I mentioned before, and a follow-up to that paper was a computer modeling of influenza. There's a paper, for example, of Flau in 85, about modeling the spread of epidemics in France, which was really numerical. I should point out there's also a paper of Dietz, and I might edit these slides a little bit. There's a paper of Dietz in the late 60s, I think, or early 70s on malaria, which is a very good computational math paper. But now the trend has really reversed. It used to be that this was mostly anecdotal, and now it's become very, very common to use computational work. And actually, a lot of papers published these days tend to be only computational. And type of case where we would see something like this is with this type of model, so network and agent-based models. Agent-based models, I'll point out that early on they were called individual-based models, but this sort of philosophy has evolved, and now people tend to think of individual-based models as the more mathematical models in there, and the agent-based models are the purely computational, computer-driven models. I won't get into this. I suspect that some of the later lectures you will see, both in the introduction and in the main course, will talk about ABMs or network models. And I'll just make the distinction. So network models are models where each individual is considered as a vertex in a network, and the power of the model is that it considers the evolution of the contacts as networks putting together people, and that's a very natural way of thinking about social contacts, and therefore these are quite interesting models. And I'll just say, there's a typo in this title I will need to fix. There's been a recent trend, and in particular during COVID, of using more and more data in mathematical epidemiology. And I'll point out that the use of data in epidemiology altogether is ancient. And actually, if you look at the field of statistics, a lot of stats has come from considering diseases. The problem that we have with infectious diseases, which this course is about, is that the data we have for infectious diseases is typically not of the same quality as the data we have for chronic diseases. So for chronic diseases, because patients remain infected their whole life, there's a much better tracking. But we're moving now towards a much better sort of collection and dissemination, most importantly, of data. So the collection of infectious disease data has been happening for quite some time, but what COVID really put forward was the need for dissemination of this data. And it's been quite interesting that the the recent trend has been for most governments to become more and more open in terms of releasing their data. And also, I should point out, there has been some good progress made with citizen science, where people, regular citizens, have taken it into their hands to also collect or disseminate data.